friends, good afternoon everyone. I am fine. How are you? I hope you will be fine. Welcome back in my channel, Dr.Satendra Kumar. Dear friends, if you want this type of videos relative to mathematics for a higher level, then you need to subscribe, share and like my videos and my channel. Today we will discuss some problems which are based on Taylor's theorem and Lorentz theorem. Now problem number first. Expand 1 upon z square minus 3z plus 2 in the region A part z modulus less than 1, B part z modulus greater 1 lesser 2, C part z modulus greater 2, D part z minus 1 modulus greater 0 lesser 1. Part C has been come UPTU 2015 and C has been come GBTU 2010. Now solution. Since fz equal 1 upon z square minus 3z plus 2, this is equal to, by factorize, z minus 1, z minus 2 on by partial fraction 1 upon z minus 2 minus 1 upon z minus 1. Now in case A, when z modulus less than 1, the position of fz equal to, since 1 is greater than z modulus, now 2 is also greater than, then we can common minus 1 upon 2, 1 minus 2 upon z upon 2 whole power minus 1 minus plus 1 minus z whole power minus 1. Okay student? This is equal to minus 1 upon 2, expand binomially, 1 plus z by 2 plus z square upon 2 square plus up to dot infinite number of terms, the expansion 1 plus z square plus z cube plus up to dot. In this series, expansion has infinite number of terms. Therefore, this is equal to 1 minus 1 upon 2 summation n is equal to 0 to infinity z by 2 whole power n plus summation n is equal to 0 to infinity z whole power n. Okay. This is a series in positive terms of z. This is a series in positive terms, positive powers terms, power terms in z. So it is an expansion of fz in Taylor series within the circle z modulus equal to 1. Okay, this is the first part. Now B part, z modulus greater than 1 less than 2. In this case, fz equal minus 1 upon 2, 1 minus z by 2, minus 1 upon z, 1 minus 1 upon z. This is equal to minus 1 upon 2, 1 minus z by 2 whole power minus 1, minus 1 upon z, 1 minus 1 upon z whole minus 1. Minus 1 upon 2 binomial expansion, 1 plus z by 2 plus z square upon 2 square plus up to dot, minus 1 upon z, 1 plus 1 upon z plus 1 upon z square plus up to dot, infinity number of terms in the expansion. This is equal to minus 1 upon 2 summation n is equal to 0 to infinity z by 2 whole power n minus 1 upon z summation n is equal to 0 to infinity 1 upon z whole power n. Okay. This is a series in positive and negative powers of z. So it is an expansion. It is an expansion of fz in Laurent series within the annulus z modulus greater 1 lesser 2. Okay. Now C part, when z modulus greater than 2, then fz equal 1 upon z, 1 minus 2 by z, minus 1 upon z is common, 1 minus 1 upon z. This is equal to 1 upon z, 1 minus 2 upon z whole power minus 1, 1 upon z, 1 minus 1 upon z whole power minus 1. Expand 1 upon z, 1 plus 2 upon z plus 2 square upon z square plus up to dot minus 1 upon z, 1 plus 1 upon z plus 1 upon z square plus up to dot, infinite number of terms in the expansion. This is equal to 1 upon z, 1 upon z summation n is equal to 0 to infinity 2 by z whole power n minus 1 upon z summation n is equal to 0 to infinity 1 by z whole power n. Okay. This is Laurent. This is Laurent series within the annulus. Within the annulus z modulus greater to lesser capital R, where R is very large. Now part D, z minus 1 modulus greater than 0 less than 1. Now fz equal to 1 upon z minus 1 minus 1 minus 1 upon z minus 1. This can be written as minus 1 upon 1 minus z minus 1 minus 1 upon z minus 1 as it. This is equal to minus 1 minus z minus 1 whole power minus 1 minus 1 upon z minus 1 as it. This is equal to minus 1 plus z minus 1 plus z minus 1 square plus z minus 1 cube plus up to dot minus 1 upon z minus 1. This is equal to minus 1 upon z minus 1 minus summation n is equal to 0 to infinity z minus 1 whole power. This is also Laurent series within the annulus z minus 1 modulus greater than 0 less than 1. Okay, student. Next question number 2. Expand 1 upon z plus 1 z plus 3 in the regions first part z modulus less than 1, second part z modulus greater than 1 less than 3. First part has been come AKTU 2016. Third part z modulus greater than 3, and fourth part z plus 1 modulus greater than 1 less than 2. Okay. Now solution. Since fz is equal to 1 upon z plus 1 z plus 3. By factorized we get 1 upon 2, on partial fraction 1 upon 2 z plus 1 minus 1 upon z plus 3 on partial fraction. Now case number first, z modulus less than 1, that is 1 is greater than z. Now 3 will also be greater than. Therefore fz is equal to 1 upon 2. Now taking 1 common, 1 plus z whole power minus 1, 1 upon 3 common, 1 plus z upon 3 whole power minus 1. Okay. This is equal to 1 upon 2, 1 minus z plus z square minus z cube plus up to dot. Infinite number of terms in this expansion. 1 upon 3, 1 minus z by 3 plus z square upon 3 square minus z cube upon 3 cube plus up to dot, bracket close. Okay. Now this is equal to 1 upon 2 summation n is equal to 0 to infinity minus 1 to the power n z to the power n minus 1 upon 3 summation n is equal to 0 to infinity minus 1 to the power n z by 3 whole power n, bracket close. It is a Taylor series within n. This is a Taylor series within a circle z modulus equal to 1. Since in the expansion of function the power of z is positive, therefore function is expand in this annulus by Taylor series. Now second part, z modulus greater than 1 less than 3. In this case fz is equal to 1 upon 2 is common, 1 upon z 1 plus 1 upon z whole power minus 1 minus 1 upon z common, 1 plus 3 by z whole power minus 1. Sorry, this is the 3 common. 3 common, z upon 3. Since z is greater than 1 but 3 is greater than z, therefore firstly we take the common z, and in second part 3 is greater than z, therefore we take 3 is common. Okay, this is equal to 1 upon 2, 1 upon z, 1 minus 1 upon z plus 1 upon z square minus 1 upon z cube plus up to dot minus 1 upon 3, 1 minus z by 3 plus z square upon 3 square minus z cube upon 3 cube plus up to dot infinite number of the terms in this expansion, then bracket is closed. This is equal to 1 upon 2 bracket 1 upon z summation minus 1 to the power n, the limit of summation 0 to infinity, 1 upon z whole power n minus 1 upon 3 summation n is equal to 0 to infinity minus 1 to the power n z by 3 whole power n, bracket close. In this expansion, the power of z is negative or positive both. Therefore, it is a Lorentz series within the annulus. It is a Lorentz series within the annulus z modulus greater than 1 less than 3. Okay, third part, z modulus greater than 3, therefore fz is equal to 1 upon 2, 1 upon z, 1 plus 1 by z whole power minus 1 minus 1 upon z, 1 plus 3 by z whole power minus 1. The terms are greater than. Another terms, the great term can be common and function convert into binomially expansion and expand binomially. 1 upon 2, 1 upon z, 1 minus 1 upon z plus 1 upon z square minus up to dot 1 upon z common, 1 minus 3 by z plus 3 square z square minus 3 cube z cube plus up to dot bracket close. This is equal to 1 upon 2, 1 upon z summation n is equal to 0 to infinity minus 1 to the power n 1 by z whole power n 1 upon z summation n is equal to 0 to infinity minus 1 to the power n 3 by z whole power n, bracket is closed. It is a Lorentz series within the annulus z modulus greater than 3 less than capital R, where capital R is very large. Now fourth part, z plus 1 modulus greater than 1 less than 2, where we take z plus 1 equal to u. But fz is equal to 1 upon 2, 1 upon z plus 1 minus 1 upon z plus 3. Therefore, it will be converted into u terms, 1 upon u minus 1 upon u plus 2. This is equal to 1 upon 2 upon u into u plus 2. This is equal to 1 upon u plus 2. 1 upon 2 is common, 2u, 1 minus u by 2 whole power minus 1. This is equal to 1 upon 2u. Expand 1 minus u by 2 plus u square upon 2 square minus u cube upon 2 cube plus up to dot. Okay. 1 upon 2 u summation n is equal to 0 to infinity minus 1 to the power n u by 2 whole power n. Okay. Now putting the value of u 1 upon 2, the value of u z plus 1, summation n is equal to 0 to infinity minus 1 to the power n z plus 1 by 2 whole power n. It is a Lorentz series in this inverse. Lorentz series in this annulus z plus 1 modulus greater than 1 less than 2. Okay. Now next question number 3. Find the Taylor and Lorentz series and Lorentz series with respect to the function z square minus 1 upon z plus 2 z plus 3. When first part z modulus less than 2, second part z modulus greater than 2 less than 3, third part z modulus greater than 3 has been come UKTU 2011. Answer: since fz equal to z square minus 1 upon z plus 2 z plus 3, on partial fraction we get 1 plus 3 upon z plus 2 minus 8 upon z plus 3. Now first part, when z modulus less than 2, that is fz equal 1 plus 2 is greater than z, therefore we take the common 2, 3 by 2, 1 minus z by 2 plus z by 2 whole power minus 1. Now 2 is greater than z, therefore 3 will also be greater than, that is 8 by 3, 1 plus z by 3 whole power minus 1. Now 1 plus 3 by 2, 1 minus z by 2 plus z square upon 2 square minus up to dot, 8 by 3, 1 minus z by 3 plus z square upon 3 square minus up to dot. This is equal to 1 plus 3 by 2 summation n is equal to 0 to infinity minus 1 to the power n z by 2 whole power n minus 8 by 3 summation n is equal to 0 to infinity minus 1 to the power n z by 3 whole power n. In this case, the Taylor series within an encircle, that is Taylor's series within a circle z modulus is equal to 2. Okay. Similarly, we can solve second and third part also. In the second part, we take common z, and in the second part of this fraction, we take 3 common. This is and expand binomially. In the third part, since z is greater than 3, therefore it will be greater than 2 also. Now in third part, we take common z in the both cases. Okay, student? Therefore, we can solve second and third part as well as part number first. Okay?